Welcome to the third video in the acontis EtherCAT MainDevice Software Implementation Guide video series. Throughout these videos, we will cover what is involved in developing an EtherCAT MainDevice controller based around the acontis EtherCAT solutions EC-Master, EC-Engineer, and EC-Simulator. Some familiarity with the acontis EtherCAT products is expected, so please check out our other videos for more in-depth product tutorial videos. In the previous video, we introduced the structure and execution flow of a MainDevice application built on the acontis EC-Master software. In this video, we'll take the next step and explore how the EtherCAT MainDevice application can interact with the process data, the core of real-time communication in an EtherCAT network. First, we will review the basic concept of how process data is exchanged in EtherCAT. Then we'll cover 3 methods for accessing the process data from the MainDevice application. And at the end, we'll show a specific implementation and demonstration. In EtherCAT, cyclic frames carry process data between the MainDevice and subdevices. As the frame passes through each node, output data is copied to the subdevice and input data is inserted into the frame. This means that each EtherCAT frame effectively contains a live snapshot of all the input and output data across the entire network. On the MainDevice side, this data is managed in what we call the process data image, a memory buffer that's updated every cycle. Here you can see how the input and output data from the frame is packed into a shared memory area, the process data image, which forms the foundation for interacting with the subdevices in real time. Now let's focus on a simplified example that we'll use for demonstrating a few options for accessing and manipulating the process data. We'll focus on a single subdevice from our development test environment, subdevice 1001, a digital I/O module with 2 bytes of input and 2 bytes of output data. EC-Master offers multiple ways to access and work with process data in your application. We will cover the 3 most relevant ones in this video. 1. Hard-coded offsets and sizes for simple testing with manual defined positions. 2. Variable names from the ENI file for more flexibility and maintainability. And 3. Generated C header file for structured, strongly typed access using named fields. In all of the methods, you start by retrieving a pointer to the process data image inputs and outputs areas. In the first method, you use byte offsets and sizes obtained from EC-Engineer to directly interface with the process data using low-level API functions. After you have the pointer, you define the bit offset and size of the variable you're interested in. Then you can create variables to hold input data or to set output data. For example, writing a new output value to send to subdevice 1001's first byte. And finally, you use the macro EC-SET-BITS to write the value into the process image. This method is very easy to get started with and use, but requires manually tracking of the variable offsets and sizes, which can change when your configuration changes. So we don't recommend this method beyond simple initial testing. The second method is a bit more flexible. Here, you will use the variable names defined in the ENI file to look up the process data details at runtime. For example, to achieve the same result as the previous example, you simply find the output variable name with the API. With this variable info, you can access the correct location in the process image without using hard-coded offsets and sizes. This makes the programming of the application easier to read and maintain, especially if the network configuration changes. The third method is the most structured and arguably most maintainable and programming friendly. Using EC-Engineer, you can export a C header file that defines the process data layout as typed structures. Here is the same variable we've been using so far. This lets you work with named fields, for example, to toggle the subdevice's first byte of output data. This approach provides a clean, compile-time safe access to process data, and it scales well across complex networks. Now we'll use this third method, the generated process data layout header file, and show how to integrate it into our EC-Master MainDevice example application. Inside EC Demo App, navigate to the My App Work PD function and add the code to toggle the output variable for subdevice 1001. Compile the example application and deploy it on the Advantech IPC used in the development test environment as the main device. We can use EC Engineer in remote diagnostics mode to monitor the live network. Once the network is up and running in the operational state, we can observe the output toggling exactly as we programmed in our application. To recap, EC-Master provides many flexible methods for accessing process data in your MainDevice application, each with different trade-offs in complexity, readability, and maintainability. For more details and assistance with EC-Master, check out our other videos in our EC-Master tutorial playlist and our documentation, which are also linked below in the description. Thanks for watching, and hopefully this third video in our EtherCAT MainDevice Implementation Guide series helps you get further along in your development of an EtherCAT MainDevice controller based on the acontis EC-Master software. If you have any questions or comments, please leave them below in the comments, or you can contact us on our website.